and a very good afternoon to everyone there in India who are attending this webinar and this expert lecture today. And today, me, Prosun Bhattacharya, and together with me is Julian Ijumulana, who will be sharing this time with you to tell you more about some important issues about global groundwater research and geospatial technology, the current trends and prospects. Okay, the lecture outline today will be divided into three parts. The part one is about KTH, what we are doing, then general background details, then the SDGs, and then the water safety plan, drinking water management, and integration of water safety planning and digitalization. And then what we see here, we'll be talking about our KTH UNICEF intervention, which you have seen in our introduction, and the digital water platform. And then in part three, the big spatial data and the artificial intelligence part will be discussed by Julian Ijumulana. But Julian, you can come fill in some aspects if you whenever you feel like. So in the first part, I talk about the details, and now KTH Royal Institute of Technology, where I'm working since 1994. So we have been working on it's been acting as a knowledge hub for a diverse suite of international cooperation, which is very important in today's world, how we can really transfer the knowledge, what we gain during our different works, what we do. So it's not very new. We have been working since 1970s, even 20 years before I joined KTH. It was very actively involved with different issues related to groundwater resources, in different parts of the world. My predecessor, Professor Gunnar Jacks, he was a world-renowned scientist working in India, and he has served as a special capacity of scientist from Sweden in the Central Groundwater Board of India, which many of you perhaps also know about, and he continued his engagements with developing countries until his death in 2019. So, and besides that, we have been working also in Bangladesh, Bolivia, and now Tanzania, where Julian is with me. So we started for about 6 years back when we started. And here our focus elements have always remained fluoride, arsenic, salinity, and also the radiogenic contaminants. And what we used to do is to understand the hydrogeological processes, which in different aquifers, and which leads to the different spatiotemporal variability, and also in terms of contaminant distribution, major element distribution, and based on that understanding to develop the mitigation strategies, because mitigation strategies, of course, is an impact, has a huge important bearing on the type of water we are dealing with, and that's a product which is governed through the nature water rock interactions in general. Just to give you a brief overview of the global groundwater resources, this is a typical map which was prepared, and this is if you see all the blue parts here, these are the major groundwater basins. We talk about the sedimentary basins, we have the groundwater basins, which are linked with different sedimentary basins across the world in different parts. And we see that there are areas where we have high groundwater recharge, areas which means all the blue areas here in dark blue here, what you see recharges which are more than 150 millimeter per annum. And then we have medium groundwater recharge and low groundwater recharge. And then, of course, we also do have areas with different complexities of hydrogeology. So and these are also depicted. If you see the Deccan part of the India, it's a high groundwater recharge again in this major part. And then we have different areas where we have where differential recharge abilities. And on together with that, we also have areas where we have local shallow aquifers. And in some areas where we see a huge amount of areas are salinity ingressed, which have more than 5 grams per liter of total dissolved solids. So if you zoom into the South and Southeast Asia, it's the same map, but zoomed in region. What we see here is that we have areas where we have areas with high salinity, especially in Indo-Bangladesh region, and also several in the western part in the Kutch basin, what we can see some this different amount of salinity ingress and with limited recharge in some of the areas where we see that low groundwater recharge areas all along the western part of India, and of course we see different variability. So on top of that, we must always remember the overall hydrogeological map of India, which shows that groundwater potential of the country. What we have in India, it shows that we have more than 40 liters per second of groundwater discharge. What we see in the Indo-Gangetic plain, right from the west to the east, and also in the Indian part of the Bengal basin, that's in the West Bengal region, what we see. And then we have very sporadic areas here in the south. We have high discharge groundwater potential where we have a high yield. And on the other hand, a vast majority of the country is in an area where we do not have prolific aquifers, but mostly these are consolidated or semi-consolidated sedimentary formations, mostly in the Deccan Traps and other regions where we have. And apart from that, we also have hilly regions which are intermittently following in the different parts of the country. So this is what we see, that we see a significant hydrogeological diversity is which affect the groundwater use and the overall groundwater exploitation potential, what we see in general. So, I mean, if we now try to see this groundwater resources availability and overall uses, so we see that if you see, I mean, figure is not very recent, but at least it's an indicative numbers what we can see here. So what we see here is the annual replenishable groundwater resources of 433 billion cubic meters overall. And if you see the groundwater draft, 231 billion cubic meter, and then what we see the natural discharge is 34 BCM, and what is balanced as a replenishable groundwater resource available is about 168. So that constitutes a total of 433 BCM in general. So if we see the annual replenishability of groundwater resource, we see that groundwater recharge from different sources is mainly from rainfall, 67%, and that's how what really makes that the climate is very important, that we should maintain that if any deviation takes place from the normal climatic conditions, so we can see a very significant outcome in terms of a huge amount of variability in the country. So these are some of the aspects what really needs to be understood even from the geospatial perspective to understand. So if you see a map and try to map out the regions where we have normal rainfall or abnormal or some sort of abnormalities in the precipitation behavior and due to different climatic impact. And on the other hand, if you see the groundwater recharge from other sources, which is 33%. So now it's important to see that how can we really replenish these sources so that we can use. So that's one of the important aspects, is managed aquifer recharge and things. So these are some of the important aspects what we need to understand. And on the other hand, if you see our use and what is the annual groundwater draft, again, this is not a very not the very current figures, but still it's an indicative that we use a substantial amount of groundwater draft is meant for irrigation, whereas a very handful, very limited is coming towards the domestic and industrial uses. So this is overall the situation in general in India. So with this backdrop, if we concentrate now on the drinking water scenario, so we have know that the access of safe drinking water is a basic human right, and also is an important component of effective health protection. And like we discussed in the morning, the Vice Chancellor of CUP, he mentioned about the threats of groundwater contamination, which affects the water supplies both for drinking as well as for the irrigation. And we have the serious contaminants, which are arsenic and fluoride and different other heavy metals and radionuclides in our water systems. And then we also have millions of people who are affected by arsenic and fluoride in groundwater. So it's very important that we have a routine for and the monitoring of these components in groundwater. And of course, we have the health impacts, as we already know, that different cancers, gangrene, and fluorosis are the most important health outcomes because of this. So now let's more go into detail about the groundwater quality. So how this point knowledge from each of the sampling points come out. So its groundwater quality basically comprises three parameters. One is the physical quality, which may and the chemical quality and the biological quantity like temperature, turbidity, color, taste, and odor. These are some of the typical physical water quality parameters. I'm just recapitulating the things which I normally teach in the undergraduate classes. And then since most groundwater is colorless, odorless, and without a specific taste, and so we are basically concerned with the chemical quality and also the microbial or the biological quality. And then we also have another source, which is the spring water or the groundwater products, which are often marketed as pure water. And because these spring waters are often also considered as mineral water or health waters in different parts of the world. So understanding the spring water quality is also very important for general use and both for drinking and also for therapeutic purposes. So groundwater, if you see it, it's actually it's not a single pure H2O, but it is beyond that. It contains several million ions, and which basically dissolve from different aquifer materials or soil particles or sediments and rocks as the water flows along these aquifer conduits, as we say, and also through the pores and fractures in unsaturated zone and the aquifer, both in soft aquifers or the sedimentary aquifers or the hard rock aquifers. And most of these are referred to as dissolved solids. So dynamics of these as solutes vary significantly. So we need to understand the spatial extent of these variabilities in general. So these are the basic backgrounds, what we need to understand through the different applications when we discuss more in detail. So dissolved solids, for example, it's again divided into three major categories. One is the major constituents like sodium, potassium, calcium, magnesium. And then we have minor constituents which are less dense, and then the trace element. These are the three different groups. And if we look into the concentrations and the range, major constituents are those which are mostly within a range up to 1000 milligrams per liter. And these are essentially in terms of cations, we have sodium, calcium, and magnesium important, and these are very important health indicators or important for human health also. And then on the anion side, we have bicarbonate, sulfate, chloride, and silica in general. And we have secondary constituents on the other hand, which have a maximum concentration limit of 10 milligrams per liter. So we have a 100 potents difference in those, the contents, but we have potassium, iron, and strontium. And on the other hand, we have the carbonate, fluoronitrate, fluoride, and boron. So secondary constituents are also equally important. Like fluoride, for example, is very important for dental caries. So it's a very important component. And then we have a range of different trace and ultra trace constituents depending on up to 0.1 milligram per liter, and then trace constituents which are less than 0.01 or in the ppm parts per billion level or micrograms per liter. So here we have a whole range of elements which are present in the groundwater. So if we concentrate on more on the trace elements, so we have different trace elements which are of health concern. There are some elements which are non-essential elements, NEE, and then these are essential elements, and then we have this potentially toxic elements, and then elements of probable essential for human health, and then other potential toxic elements or other PTA which are undesirable if excess. But there are no statutory limit has been set. So these are the classification of different elements, non-essential elements. Like even here we can see that right from ruthenium, rhenium, palladium, indium, like that. And then we have thallium, bismuth. So these are the elements which are non-essential elements. And examples of essential elements, of course, is molybdenum, selenium, cobalt, nickel in very low concentrations. phosphorus, and so on and so forth, and then potentially toxic elements. Here comes the like elements like arsenic, cadmium, nickel, chromium, lead, aluminum, manganese, iron. And on the anion side, we have sulfate and nitrate, which are important. And elements of probable health, here we have beryllium, scandium, tin, tellurium, lanthanum, arsenic, barium, strontium. So these are some of the things. And other potentially toxic elements, of course, include beryllium, vanadium, barium. So we have a wide range of chemical elements which are mobile in groundwater environment. So we can have to really diagnose the occurrence of these elements. So like the problem which we are talking about in Punjab right now. So there is a huge boom of quest for understanding the hydrogeochemistry in the region. So this is very important, that how do we can really map the occurrences of these elements in different classes, so that we can talk about. And here in this map diagram, we see the relative percentage of these different elements in groundwater matrix. So now if we assume that we have this scenario of groundwater contamination, what we can see that there are two types of contamination. One are the natural sources, which means the natural mobility, and on the other hand, we have also different point sources, line sources, and diffuse sources. So diffuse contamination is mostly which comes from the natural sources, like the aquifer matrix itself has an inherent components of groundwater, different elements which are mobilized due to our abstraction um, scenarios, what we see. And then on the other hand, we can be beyond this, we can also have beyond this natural elements, we can also have diverse suite of chemicals which can leach into the aquifers and prove to be toxic to humans. So these are the two sets of diagrams. What we can see that we have this agricultural runoffs can lead illegal dumping of wastes. Municipal can impact the groundwater quality in general. But this again, if you see compare this one in terms of space, we need to really understand what is the variability of this region, which is marked with the agricultural region, with the urban runoffs from the road runoffs. For example, we have diverse suite of metals which comes out from the road wash, or and then we have the sanitary landfills, so on and so forth. So and then how do these components which are percolating downwards, how they impact the groundwater quality in general. So and then not only a point information on a specific time period, but it should be understood in a much more holistic perspective when we talk about in terms of a time series. So that so during the peak agricultural season, peak where we are using huge amount of pesticides and other agrochemicals in our fields. So what is the impact of these agrochemicals into the groundwater system? So we need to have a much more holistic understanding. And then on the other hand, we also have the saltwater intrusion in coastal areas, specifically where we can have this. If we have excess, if you pull out more water, so you are more likely to saltwater intrusion to take place. And so these are some of the typical impacts of the overall groundwater contamination scenario. So so it's really important to see that how we can really integrate these special knowledge into the sustainable development goals, and so that we can really enhance. Water is one of the important aspects, which is the SDG 6, clean water and sanitation. So this is important. So this is for the first time when in the SDG 6, which has highlighted the overall perspective of water in a broader sense. So we have 6.1 drinking water scenario, and then we have the sanitation and hygiene, which is again a function of the water availability. And then we have the water quality itself, water scarcity in regions where we have very high low rainfall or high evapotranspiration, so that we are losing water due to less vegetation, so on and so forth. And this, which really water resource management perspectives, So in an ecosystem, so if you really look into these aspects, so each of these blocks or the tapered and trapezoids, the boxes mean that we need to understand in a spatial perspective what are the variations. So what is the impact of groundwater abstraction from a point to its surrounding areas? So we need to really understand the entire process. And to do that in the SDG, when it was started in about 6 years back now in September 25th. So we have 17 goals, and water is actually cross-cutting in each of these 17 blocks of SDGs. So we have a total of 169 targets and 230 indicators, and within that, so that to achieve within an overall span of 15 years. And interestingly, within the SDG 6, and it has already recognized arsenic and fluoride as two important contaminants which are actually impacting human health globally. So we need to really find accelerated methods for mitigation of these components. So this is actually a very important topic. So what emerges out of this thing that we need to really think about the water safety plan, or WSP. It is actually talking about the safety of a drinking water supply system, which uses both a comprehensive risk assessment and risk management approach, and it again encompasses in all steps in water supply from its catchment to a consumer. So this is a schematic view of how water is understood in a water safety planning perspective. So what we see that we have the water sources, which can be the natural aquifers, it can be river water, or it can be sources of fresh water. And then if you have the treatment, then we have the treatment innovations. And then once treatment innovations, if you have treated the water to absolute cleanliness, so you have cleaned, and then one is poured into the distribution system, which is again a factor which is a point where the contaminants can re-enter the water resources, which can reach the consumer system. So the entire chain of this system needs to be understood, and within the entire chain, we need to assess the water quality and the availability and accessibility. And when we talk about water sources, it is again a function of geospatial application. So we need to understand what are the sources right from the catchment to the point of abstraction. So that's a very important thing to understand. So water safety plans, for example, it has three most important components now. So what is being guided essentially by the health-based targets, that is the WHO, the latest drinking water guidelines 2017, and it also emphasizes drinking water supply surveillance system. Surveillance system means where you can have an assessment of the overall system, and then we have the operational monitoring, so that source water monitoring and the management. And then system assessment in the second part, in a sense, means that it also needs that whether the drinking water supply chain up to the point of consumption can deliver a water of a quality that meets health-based targets. And then if you see a specific problems which are identified through this monitoring exercise, so we can control identify the different risks, and so that we can restore the compliance with the specific health-based targets. So right now, what is the major, the Punjab scenario, for example, if we reflect back on the current situation in Punjab, for example, what we see that now there is a great interest in understanding the hydrogeochemistry of the region. So we have started looking into the water quality parameters. Now the question is that, yes, we are doing water chemistry on one point time. It is just a point measurements of the informations of the water quality parameters. So that gives us a specific idea about what are the specific contaminants. So what we actually are missing here in the perspective that we don't have a long-term time series monitoring, which we need to think about and try to start off the things. And then we also have a system of management and communication, which is relatively missing in the overall practice and surveillance. So monitoring and surveillance, these two are linked together. And so there is what is essentially seen, that since these two are not very well developed in water safety planning perspective, so we don't really see the health-based targets. So now you're right. So that is one of the major reasons why we see a huge amount of impacts of groundwater based. It can be basically it can be due to use of groundwater for irrigation, so we our food crops, and also on other hand we are also using different various types of agrochemicals. So what are the potential impacts of those agrochemicals? So those get unnoticed and they are getting into the food chain and causing diverse suite of health complications. And one of the examples what we see that in Punjab, for example, we have this huge amount of boom of cancer in the recent past. So that's been highlighted over the media, and several things like the Cancer Express, for example, the patients going from Punjab over to say Ganganagar Cancer Hospital. So that's very alarming. So how do we really check these happening so that our next, to ensure the future generations, our children, how they can be. So that needs, of course, a monitoring and plans of communication, so that we need to see that how can we really cut off these contaminants to a. So and that also needs a strong and comprehensive legislative national policies and framework for enhanced drinking water management. And here I would also like to add drinking water and agricultural water management both. So this is an example of what I would like to call system assessment in the geogenic contaminants perspective. So groundwater, as I mentioned, is a natural, it contains naturally occurring chemical elements, and in different geological settings, we have different natural contaminants at levels which are toxic to humans and also to plants and other. Um, in the trophic cycle, it impacts. So water quality assessment is important there, and we need to gather more evidences of the potential impacts on the other environments. Now, for example, if you see that we have the geogenic contaminants here, we have natural mobilization process, and on the other hand we have also technically enhanced mobilization. This means that we have different areas with mining, where we are actually mining the different metallic ores and beneficiating those metals, and then we are trying to release those not useful materials into the in nature, in nature. So which what happens, so it actually contaminating both the sediments and soils. It is impacting the hydrosphere, and also and part of this are also released into the atmosphere, which again returns back to the earth. So yes, and the third level, what we see, what are the impacts we see in the impacts in the water resources. We see impact on the agricultural producers. We see impact in our fisheries, and in different livestock. So these are the different. Arsenic, for example, has been one of the elements which has been widely studied in detail across the different continents, and these are most essential for the overall human health and well-being. So that's a important factor. So again, I will reiterate that yes, we know that the fluoride is. For example, in Tanzania, we are talking about the different irrigation and the plants, like we have this maize and other food crops which are grown. So if they're irrigated with high fluoride regions, both from the sediments, both from the surface and due to irrigation water, we have fluoride, arsenic, salinity, and radionuclides. There has been a recent PhD thesis from which has been in Pakistan, for example. So they have been working on how arsenic and salinity are impacting in the Punjab region of Pakistan, especially in the Punjab, in the both in the Ravi and Chenab Doabs in the region. So how they are intricately associated, the mobilization of arsenic into. So these are some of the typical examples what I can give. So I'll just give you a non-conventional example. This is from based on our studies in Argentina, and this was done by Ana Olona Alcaine. So she has worked on a region in Argentina where we had, this is a typical volcanic ash bed, what we see in Argentina. This is a picture which was taken by me way back in around 2002 or 2003. It's a thick volcanic ash bed which has diverse suite of chemical elements. So like arsenic, vanadium, molybdenum, uranium, so on and so forth. So, and how does this leaching of these different elements cause contaminate the groundwater sources in the in water? So, and here the mechanisms has been understanding the absorption and desorption processes, precipitation, dissolution, and also redox processes in general. So all these processes do vary. They are not static, so they vary in space and time. So we need to understand those mechanisms. So these are some of the important aspects of where geospatial technology can really assist us in deepening our understanding of the mobility in general. And then the secondly, about if we think about the mining areas, was oxidative dissolution of metal sulfides from primary sources, and then volcanic glasses in general, and then adsorption on secondary iron, aluminum, manganese oxide hydroxides, which have, if you have high surface area and positive charge at low pH, how this will move. And then we have desorption from iron oxide minerals at high pH, where the point of pH is more than the point of zero charge. So that facilitates release of these contaminants to the groundwater. And interestingly, we also need to monitor the spatial variability of the changes in the pH and the redox conditions to understand the mobility and also the impact or the influence of different competing ions in the for groundwater. There's the trace element contaminants in the groundwater resources. This is again one of the example of again major ions, which we see a diverse, a quite significant variability here. What we see in the two areas, one is Kemukamu and Interdente Alvea. These are the two regions where we have studied. So this is one of the study results. And this is exactly what I would like to see, that even in Punjab, for example, we need to understand and try to plot these variabilities in general context. And then these are again the trace element constituents. What we are talking about, I was talking about arsenic as one of the important constituent, boron, uranium, vanadium, molybdenum, besides iron, aluminum, manganese. So these are the basic components. So, and each of these variabilities, what we really see that these are from the individual wells and the very diversity in the diverse concentration in the groundwaters. And then we also try to see that, understand the mechanisms of mobilization, to see that what is actually impacting. So we have this is a bivariate plot which shows relation of arsenic with pH, bicarbonate, electrical conductivity, and then co-occurrence of different suite of contaminants, arsenic vanadium, arsenic fluoride. What we see very good positive correlation trends is what you see over here. And then when you see uranium, which shows some sort of heterogeneity. So we need to interpret these things so that we cannot leave these plots just as we need to find what is the specific relationship between these individual components. So these are, as an example, I'm projecting this so that we try to impart this knowledge to all of you so that we know. Now, spatial distribution, this was my concept of spatial distribution when I started this work. And when I now sit with Julian and try to plot this, so I see that there are so many. I mean, these are just a small information, bit of information. This is just the small surfer plots which are shown. That what we see here, if you see that arsenic in this set of wells has very high concentration coming up to 500, 600 micrograms per liter, and then the concomitant variability in fluoride concentration. So these two elements are spatially related. And then of course we can also see that boron, this is also high in the same pocket. So this gives an indicative of how the way these vary in specific wells within the specific depths of the wells. So this is something which is very important to understand. On the other hand, and if you also see that there is also a similar parallel behavior of bicarbonate in all these wells. So I mean, this, you can really translate this information as a primary data analytics so that you can understand what are the interrelationship between the different water quality parameters and how do they drive. But this is not spatial analysis. So this is just an indicative of how our chemistry is varying in the region within the different wells, where we compare the wells of identical depth, identical in different wells. And this is again another set of pictures which show vanadium, iron, and aluminium. So this brings a more complexity. So which at some point of time it's really difficult to explain these diversities, because within in spatially we can have diverse drivers in the subsurface which govern the, for example, iron dissolution is one important, or oxidation. So what we can see that why there is no dissolved iron is high here as compared to here where we are arsenic mobility. So we need to understand these mechanisms in much more detail. So once we look into these things, so then we can see that these are again some of the specific samples where we do the calculation through understanding the hydrogeochemistry, the saturation indices of different groundwater samples, and the principal minerals which govern the mobility, control the water chemistry in the regions. Like for example, Ne25, which is yellow, which has a high pH value. So these are very close to the point of zero charge, which means that any arsenate, for example, which is the primary form of inorganic arsenic in groundwater in this terrain, can be mobilized to groundwater when the point of pH increase is close to the point of zero charge. So then the water arsenic is mobilized into the groundwater. So, I mean, that is the short background of the hydrogeochemical approach to understand. So now what we need that, I mean, these are the things, because these are the wells which are being used by the people for drinking water purposes. So we need the four pillars which the implementation of drinking water safety comes in, that how we interlink groundwater chemistry and the drinking water safety. So we need to have the technology. Firstly, the detection and extent. Again, I come back that we have the field-based methods, arsenic test kit, and different probes, and then we have laboratory-based advanced instrumentation like ion chromatograph, ICP OES, ICP mass spectrometry, and more sophisticated analytical results. And then once we have this data, we need to get into the spatial data interpretation based on the different softwares and how we can develop to look into. Like for example, in Punjab, now we need to have this diverse suite of data, which comes from both from the primary information for phase from the field-based investigations, then lab-based, and then again try to link up with the geospatial map, I mean remote sensing maps, for example, to see what are the areas, are they water deficient in general per se. So there has been some important papers which have come out of since 2008 by AWAG, where Michael Berg and his group, they're working quite systematically on the groundwater assessment platform, where they're trying to gather such informations on their database, where to understand. So that is one aspect. And then based on that, we have to build up the spatial data. Okay, if you have this set of geospatial setting, so these are the maximum concentration limits, and how we can really use those information to develop general artificial intelligence, or at least come up with a machine learning approach to understand. And secondly is the capacity building, so that we need to make these technologies transfer to training of the water resource managers. And one of these, I think this is one of the important uh, reason why we have this Atal faculty development program, that how we can really transfer this knowledge to all of you, so that we can move to the next phase, where we can, in terms of when we talk about data monitoring, accountability frameworks, and then to understand the spatial data in general. Once we have a real general spatial data, then we can have the real-time data, which means that what is happening now. So we have this measured data from the past, and what is it happening and how is it varying, right, from in different parts of the years and over the years, so that we need to make a more sophisticated real-time data planning. And of course, we also need a diverse suite of, like, I mean, it's really important that we need to understand the different patterns in these data, how they're varying, and then based on that to really make some of the important decisions and that's both by the academia, private sector, public sector, and the community, and also national governments who are the responsible for the drinking water and for the water quality monitoring. So in India, I mean, there has been quite because of my work since late 1990s. So we have been looking into the national rural drinking water programming, and then we also had this rural drinking water and sanitation initiatives which came out way back in 2015. So these are some of the guidelines and of National Drinking Water Program guidelines, and also the innovative technologies which have been put forward over the years. So before we go into those details, if we look into slightly, I'm giving you a touch of national water policy, which this is a part of the lecture which I gave during the BIWF summit last year, where we talked about national water policy, how it evolved from 1987 to current. So in 1987, when the first national water policy was drafted and enacted, so it was the water is a prime natural resource, basic human need, and precious national asset. And then in the same document, when we talk about need of a national water policy, we talked about it was defined as another important aspect. It's not the important aspect. See the use of the words. So this is the concept, because it is evolving. So it's really good that water quality aspects was already highlighted way back in 97. So what we are talking today is advancement of this approach, what the government initially had thought about. So they also emphasized improvements in the existing strategies and innovation in new techniques, which based on evidence-based science and technology to eliminate the pollution and the groundwater sources for improvement. So this was already there since 87. So 30 years have passed since then. So where are we now? So and then they also highlighted the science and technology and training have important roles to play in water resources development. So you see, I mean, this is as a follow-up of this, we came with the national water policy that was April 2002. And here we talk more about water resource planning, where we have the water resource available to the country brought in the category utilizable resources. And then we have different methods, interbasin transfers and other rooftop rainwater harvesting, and those interventions were also proposed during this step and during this national water policy drafting. And then water resource development and management has to be planned for hydrological units from a drainage basin perspective. Now, if I see and draw a corollary to what is happening in Tanzania, for example, you will be talking more, Julian, that we have different water basins, and these water basins have been defined individually based on the availability of water, the amount of recharge, discharge capacities, and so on and so forth. So and all of these aspects must be incorporating the quantity as well as the quality based on the different environmental considerations. And geology is one of the important part of it, which really governs the groundwater quality in general. And then water allocation priorities was also highlighted in this water policy 2002, where in this case it was in planning and operation of the systems. Water allocation priorities were defined. Drinking water was given the top priority, followed by irrigation, hydropower, ecology, and agro industries, and navigation and other uses. So these priorities were not very static, but they are always, we need to develop and modify them depending on the current situation. And of course, in a very important point, which was adequately addressed in this, was that safe drinking water facility should be provided to the entire population. So what we are talking today is not 100% new. So this has been there in the national water policies. So we need to enact those policies and how these are evolving. So now the next Rashtriya Jal Niti, that's the National Water Policy 2012, it talks about water framework law. This was actually in analogy with what we have the European Water Framework Directive, WFT. So that's some sort of a replication of that approach, what India has already started. So it's really a very good document which was already presented in 2012, about almost 10 years back. And here we also talked about, they've talked about the water supply and sanitation aspects, the diversities in urban and rural domestic water supply from the surface water sources in conjunction with groundwater and rainwater. Of course, it has been severely impaired because of the droughts and the climate change scenario over the past 10 years. So we are not in a position to catch up with this. So that this is very important to address these complications which has been arising due to this sudden climate change impacts and things which govern the water thing. Julian, you keep the time for me. So, and then the national water, and this is the latest one, which is still in a draft framework bill, which is even more detailed. And this is 2016 when we have. So here what we see that we talked about the preservation of water quality. And then when you talk about provisions of the Environmental Protection Act 1986 and Water Act Control, that is the first act which came in India, 1974, enforcing recycling and reuse of water, minimizing generation of waste, and most importantly, reducing non-point source of pollution. So these are the important aspects. So whenever we talk about groundwater, we need to understand the spatial distribution of this non-point source of pollution if you want to safeguard the groundwater resources for drinking purposes, and the water from different wastes. So how do we really manage those things? And then water quality and streams, rivers. Now we have new add-ons on these. We have the pharmaceutical wastes, we have the PFAS elements coming up. So these are more additions to the complications rather than simply geogenic contaminants and other naturally occurring contaminants. So these are the important things. So overall, we need to really think about an application of precautionary principles so that we can really safeguard that. And then of course the responsibility, the polluter pays principle, which is one of the key in the draft water framework bill. So now I was trying to link into the Jal Jeevan mission again here. So water safety planning and how water safety planning can be accomplished in Jal Jeevan mission, where you envisage this is a national Flagstaff mission of providing water to each and every household. Okay, based on ground. I mean, in many parts of India, we can have only the groundwater resource, which is the potential source of drinking water. So that how that we can really monitor these groundwater sources to move into the thing. So this is again an example of how we can actually link up different policy documents. So here we see that different sector documents, how the different policy moves out from the parliament, cabinet, ministry, and the different implementing agencies. And then we need to look into the. So overall, this is an example from Bangladesh, what we are doing right now. We need to have an approach of system strengthening approach broadly, where we do a understanding the existing policies, protocols, and different guidelines, developing different manuals, and then developing the context and technology specific strategies and different protocols. And for groundwater monitoring and hydrogeologic aspects, we need to have the aquifer characterization, hydrogeological monitoring, real-time mapping using digital water platform, what we are doing. So, and then capacity enhancement in different aspects. And then this was again done in from the arsenic safe community perspective. So again, this is a comprehensive scenario how we can build up a society, a community in a region where for arsenic safe water sources in general, and how it can be scaled up from a small scale, from a village to a union level, to a district level, to a upazila level, and to a district level. So this is just an example to demonstrate. So, and that was the end of the part one. So in part two, what I would like to envisage here is right now we are actually working with the KTH UNICEF together interventions for the implementing the sustainable arsenic mitigation process to be coming, and then the digital water how digitalization can enhance this understanding. of the variability. So what we are essentially what we are doing here in this intervention technique, what we are doing, we're reviewing the different policies, protocols, and regulations, review up to date, and then strengthening the capacity of the critical masses of drillers who are actually drilling the wells, and then understanding the integrating the SASMIT protocol in the DPHE, the Director of Public Health Engineering in UNICEF Arsenic Safe Village Union project. And then finally, we are also supporting the government of Bangladesh to establish a registration and certification system for both public and private drillers. So this was actually the original sediment color tool which we developed, and this was one of the key deliverables out of the SASMIT Sustainable Arsenic Mitigation Project. And then based on this understanding of the local drillers, so these local drillers will be given the water wells. And then we also have the collaboration with the health department for patient management scenarios, so that how we can really get into the thing. So that was exposure and mitigation. So the overall target, of course, has been that we have had significant progress in terms of characterization of the source, understanding distribution of arsenic processes, mobilization and sediment water interactions. But the mitigation aspects has remained to a gross extent unexplored and unaddressed. So, and this has actually resulted in a huge gap between the exposure and the pace of mitigation. And so SASMIT was therefore very important that it gave a simple, cost-effective option which could be easily acceptable by the people and the installation of safe tube wells together. So over the time, there has been a number of different mitigation options has been given, so that we have this happening. And then evaluation of different options, we see that the tube wells were the most important options which were given. So none of the interventions in terms of filters, rainwater harvesting were operational to a major extent. So only the tube wells came up as one of the important safe water source for the population. And it also has a linkage to the societal needs. So that's also a GIS mapping of the area from the different point sources and the sources of safe drinking water. And so what we see that based on a social survey in 96 villages, what we looked into found that 18% of the tube wells were safe with respect to arsenic, and it was actually translated into one safe tube well for every 85 people. And there was extreme variation in safe water access, from no access to up to 91%. So there has been duplication in the distribution of the safe water safe water provisions in the regions. So tube well as a mitigation options had emerged as one of the key parameters. So where depth of the tube well is a key parameter for understanding tube well installation, and it was linked with the groundwater quality, abstraction technologies, simple handheld wellheads, and the cost of installation, they were very low. And then in general, the governmental wells, they were using deep wells up to more than 250 meters, very expensive options. And then compared to the safe demand, the deep wells were still not very common and very low as this was beyond the affordability of the local communities. And shallow tube wells less than 80 meters were mostly at the risk of arsenic contamination. So it was important to know that the all shallow aquifer mostly were arsenic contaminated. So we need to understand what is the dynamics of arsenic as we go with the depth of the aquifers. So it's important that this important objectives what SASMIT had after this analysis of the situation analysis. What we find that installation of safe tube well, most important task is to identify the safe aquifers, and which will remain as a source of safe water supply, and then explore the overall subsurface aquifer system to identify and delineate and monitor an aquifer in terms of both arsenic safety and also manganese safety. So because one important factor also came that many of the groundwaters also have had high manganese concentrations. So in order to avoid future complications due to manganese impacts of manganese on cognitive health development. So we need to look into the manganese issue in groundwater resources as well. So what we did actually, this is an important seismic innovation about understanding the piezometer local, the hydrogeological scenario understanding. So we have the different set of piezometers. We have this 6 piezometers in the overall in the regions, which is designated as P1 to P6. P6 is the last one because this was the intermediate between the deep and the shallow aquifers, which was came out as a seismic innovation, that these are mostly at the depth of 100 to 120 meters, and the deep, which the governments, and even I think it's also in West Bengal, where we have deep wells as the public wells. So and these wells were monitored for both in terms of water hydraulic head monitoring and also water chemistry monitoring over a period of 4 years. So what we see here, so in the EPSC project, we extended this concept beyond further on a national basis, but still focusing on 3 regions. We focus, one is in close to the Meghalaya border in Asasuni in Sylhet district. Then we look in Daud-Kandi in Comilla district, and again Asasuni in the Borishal division in southern Bangladesh in coastal belts, where we find. So, and these are the different abundances of arsenic in about 66% contaminated wells in Asasuni. And then we have around 33% contaminated wells in Goainghat in Sylhet region. And then in Daud-Kandi, we have around almost 50% contaminated wells in the shallow wells. So these are some of the situation analysis in the region. So based on that, we need to understand this in a GIS perspective and also in terms of understanding the drillers mapping. So what we did, the drillers mapping, drillers mapping was essentially based on understanding the drillers hubs. These hubs are actually the hardware stores in different villages or in different communities, where they go and purchase different hardware items like fuel heads and other things. So we see this drillers mapping, and most of these drillers were affiliated to this drillers hub. It's almost identical to professors affiliated to universities, right? If you want to meet a professor, you have to go to a university. So it's exactly like, if you have to identify the drillers, you have to go to the drillers hub, because that is where they get their tasks to do. So when you get, and so we could actually map these drillers, and then we did some interview with these local drillers, and based on their practice, these maps were prepared and put on a GIS overlay, and this demand shows the safe depths for all the red sediments. There's the aquifers with low arsenic concentrations, which they are targeting, and then these are the general abundances, and then consideration of different social abundance. So this were, and then the next step was the piezometer installations and at different depths. And then we are using the Asmitas digital application for safe aquifer delineation and integration of the arsenic safe union and SASMET integration through digital platform, and so these were some of the next. And this is again the details of the driller mapping. So we identified 29 hubs in Goainghat in the north, and then 13 in Asasuni and 13 in Daud-Kandi. So they were, and then these are again so different drillers codes and different drillers numbers. So these are the drillers mapping, and then subsurface geological information, as you see here. So here we see different distribution of the oxidized layer in different parts of Daud-Kandi region, and sand clay layer distribution in the regions. And then the sediment color tool, which was developed based on the relative risk of arsenic in the different sediments. This was used through a digital application, which was developed since 2019 onwards, 2018, 2019. And this was Asmita's arsenic mitigation at source. And here what we could do actually, instead of writing the sediment lithologs, we are directly documenting all the lithologies into this application directly in a series. And the result was that we could really make a digital litholog. And together with that, add-on was that we could also decode the sediment colors to put besides this, so that we could really brand them with respect to the sediment, with respect to the safety in terms of drinking water, water safety plans. Okay, so then I think, and then this was scaled up, for example, for real-time monitoring and dynamics. And this is again a field scenario of what was done. And I mean, this is again the local drillers who are in operation in the field, and they are collecting the the sediment, scanning through the NIX system. NIX is an handheld tool for for registering the sediment color with the help of the app. So we are actually documenting the sediment color, which is coming right through, connected through the Bluetooth here, and getting registered on the, and this is actually essentially replacing the traditional handwritten lithologs in the general. The next step which comes from here is that we need to have this interface. So we need to have Asmitas as a data capturing hub or a tool, and from the data capturing tool we need to go ahead with this aquifer mapping program. So this is more regional in a way, a regional, so that we can have a series of data which can feed in, and we can have a diverse cross sections of the sediments in the region, so that we can collect as much information as possible through the application of this digital app. And then, and this is again, and then if we want to systematize the data and real-time information, so we need some more IoT devices for understanding the water quality information in real time, so that we can make into business interface cognitive services, so that we develop a more important knowledge management system for data visualization, so that the users or the policymakers, they can see the current status of the groundwater composition. And this is really very ideal for Punjab specifically, when there is so much of great interest, I mean, within the state, at how we can really build up this system for groundwater management. And then, and perform water quality monitoring, modeling also in terms of surface water, groundwater, and using the different data inputs and for the machine learning framework. And then knowledge co-creation with other local stakeholders, like for in the agricultural sector, in the health care sector, so we can have intersectoral collaborations to understand the disease prevalence and also the water quality issues. And then the last one was also the Asmitas and GeoGIS. GeoGIS is a program which was actually designed by the Rumble concern, and we are collaborating with Rumble. So who are actually using this Asmitas borehole database and the hydrogeological data, and to feed into this GeoGIS platform to make a comprehensive understanding of the aquifer system. So it is actually the local drillers which is giving through the Asmitas app, goes to the GeoGIS model, and from there we have the individual bore logs, and then we can also have the visualization of the different geological formations in the region, which will get back to the feedback to the Asmitas app, and then that will reach. So it is a loop which goes via this, so that the local drillers or the policymaker, they can be benefited out of this practice. So I think I'm getting closer to my end of my section. So the consolidation of data is important for the to-hand application of big data tools, for both for national and transboundary data sets, like in West Bengal, Bangladesh, for example, one, and then also the Punjab case from West Bengal, from Punjab, India Punjab, and the Pakistan Punjab, how we can think about the variation and variabilities in groundwater composition, and co-creation of solutions and value additions from the existing data sets. So understanding the existing data sets, how we can reinterpret those data, so that we don't need to have a absolutely new fresh data, but we can see from the historical data, get the new data sets which we are getting through the different. And I know that CUP is working quite intensively right now on understanding the groundwater chemistry in different parts of Punjab, so how they can be utilized in the whole perspective of drinking water safety and groundwater quality monitoring approach, and then understanding which parameters and all, and then of course the application of data visualization. With that, I thank you for my part, and I would now hand over to Julian. Sorry to keep you waiting. Thank you. I think we take the question answers later on.
Yeah, thank you. I will take up on this part, and it's all about the big data and artificial intelligence. And specifically, I will talk about the spatial data and the deep learning approaches in order to understand the contents or the information contained within the spatial data. Yeah. So what is the spatial data? Basically, it's an observed event whose location or position is implicitly or explicitly stated. And in that case, it can be either the X or Y or latitude and longitude. But mainly, it is any kind of data whereby the location becomes a part of the data set. And in this case, if you look into this diagram here, you have the coordinate system, whereby every event we observe is located on one of the systems. So we have either it can be a global system, or it can be the local system, depending on the location where you are. But here we have this concept of spatial analysis. In this case, we look at the properties of the observed events at location I in relation to that observed at location J. So, and this is very, very important, because that's when you can even understand the properties, and also you can formulate some hypotheses and understand the system itself. So we have two types of spatial data. We have the vector data and we have the raster data, but all this is just from the same real world. And for the case of this vector data, the objects are represented as point, lines, and polygons, whereby in raster data, the real world is everything is represented on a pixel or the field cells. And we have this concept of the spatial data model. Basically, when we talk the data or spatial data within the digital environment, we are talking about how we represent this data. So as I said before, that for the vector data, the objects will be represented as point. For instance, trees, they will be represented as points. Linear features like road, rivers will be represented as lines. And aerial features like what Professor Prosun is talking about, the groundwater basins, can be represented in the GIS system using connected points. But for the case of the raster data model, everything is recorded on the row and column. So here we talk about the signatures or the reflectances of objects, which are transformed into these signatures, so that it will represent a point, line, and aerial features. But where do we get this spatial data? There are two basically approaches. We have the ground-based approach, and we have remote sensing-based approach. So in the ground-based approach, we have the direct, measurements or observations are taken direct in contact with the target. Okay, we have these conventional methods, technologies like theodolite total stations, GNSS instruments, whereby you are in contact with the target, but finally you end up with getting the observations or measurements. But for the case of remote sensing, yes, we take observations indirectly with the target. So in that case, here we have a key component, which is image data. Okay, and then from the image data, that's when you can get observations and the measurements. But the final product, when we are talking about GIS, I mean a digital environment for spatial data, then it is the spatial database. Okay, it contains a huge amount of data, depending on the, I mean, they can be at a point in time, or they can be over time. So the concept of artificial intelligence basically applies on this spatial database. Now, what is GIS? Basically, from the general understanding and maybe experience, it's all about the computer-based system for collection, storage, manipulation, and visualization of spatial data. Okay, and in that case, here we have the software, okay, which is very, very important, dedicated software. And we have the hardware, that means you need powerful computers. And we have network, and in this case, you need to communicate information from the collection and to the user. So that means you need a powerful network and so forth. And then you have this data. This is what I'm talking about. But also we have this people, and this is the challenge, because GIS is a bit wide, and it needs experience, and it needs people who are trained to perform the spatial analysis. So the presence of these people, maybe the rest of the components, it would be easier. But also the last one is the procedures. That means you need some procedures, and these procedures should follow the semantics depending on what you want to do. I will talk more about this in groundwater studies. So, but now what is the key component in the spatial data is the spatial data quality. Okay, and in this case, I usually refer to this international organization for standardization and definition. But in a layman language, quality refers to the good or useful things. That's how anybody can answer. But for the international organization for standardization defines quality as the totality of characteristics of a product that bear on its ability to satisfy stated and implied needs. So in that case, quality should be assessed by the fitness for use. And in spatial data, we talk about the precision and the accuracy. So if you look at the example of this figure, you will see that everywhere you need the reference, okay? And whatever you observe, it should be tested against the reference. So maybe in terms of groundwater, the threshold, which is, I mean, it's the maximum permissible value, maybe can be considered as the reference. So that means whatever we observe at the source should be tested against the reference to see if, let's say, it is close to what we observe, or it is above, and so forth. So in that case, you can assess the reference. So in the problem which we encounter when dealing with the spatial data quality is the reference, because sometimes this reference is not yet, I mean, it's just a provisional value. For instance, in drinking water, it's just a value which has been proposed, but there are no enough research about it, but it's just a provisional. But in other applications, like let's say position, then here maybe you need a point. I mean, we need a point, I mean, observation which has been collected from superior methods, and then it can be used as the reference from what you have collected. But now, when we'll talk about the spatial analysis, it's just one of the components in GIS that we collect the data, we store the data, we manipulate, and we analyze, and finally we disseminate what we disseminate. We visualize, and then finally we disseminate to the users. But here, the standard operational procedure basically is looking at the observation, at one observation in relation to other observations on the same target. Okay, and here we have this specific terminology which is used in spatial analysis, which is exploratory spatial data analysis. And in this case, you first of all, before you subject your data into rigorous operations, then you need to determine the nature of the distribution of observed events. Okay, and in this case, you can identify the clusters. You can identify if the observed events are sparsely distributed or they are randomly distributed. So basically, it gives us indication about the processes which could be taking place at those particular locations. And finally, you will also determine the locations with the extreme value events. And in groundwater quality studies, this is very, very important because it gives us an indication of what is happening in specific areas. And by so doing, you can formulate hypotheses. Okay, let's say in areas with extreme values, you can just formulate an hypothesis, but some other areas whereby we have low values, you can also formulate another hypothesis, because whenever you come up with this condition, it means there is heterogeneous processes or stochastic processes contributing to this one here. We have the final one. This is hypothesis testing, that is through spatial modeling. This is beyond what we are used to, because you incorporate the spatial dimensions of the observed events in order to account for the spatial effects on what you estimate.
Hello?
Sorry?
No.
Okay. So, but basically here, what we are talking about, all this is applicable to ground-based and remotely sensing-based spatial data. But here for remote sensing, it is very, very important to note that in remote sensing, we work with the satellite images. Okay, and in that case, if you are extracting information from the satellite images, then there are some methods as well, artificial intelligence approaches to extract information from the image. Okay, and in that case, either you can use the pixel-based or you can use the object-based oriented. But finally, you will have to do spatial analysis. In that case, maybe to integrate what you get from the image to GIS, to what is existing, and then you try to monitor what is happening. And the good thing with spatial data analysis, it means you integrate different data sources from different data sets from different sources. And by so doing, you can optimize the understanding of what is happening. But here we have the standard irregularity conditions, which should be observed, especially when you are exploring, when you want to select which method, which direction, either spatial analysis or simple classical or standard analysis. But basically here, all these standard methods were developed based on these standard irregularity conditions. Okay, that means there is no systematic bias in the observation, in the error terms. And also there is constant error variance. That means there is no heteroscedasticity, no error correlation, including no spatial autocorrelation. There is no endogeneity. That means every exploratory variable is uncorrelated with the error terms and the normality in the error terms. So all these are the regulatory conditions which were upon which the methods, classical methods, are used to do some studies or to do research. But you need to in the spatial analysis, this is the null hypothesis. That means you have to test the validity of every assumption. Now, that is when the concept of spatial statistical analysis. And basically here, this concept is based on the Tobler's first law of geography in spatial analysis, that everything is related to everything else, but near things are more related than distant things. Okay, and in that case here, you have to find out on how you can incorporate the neighborhood of what you have observed at location X. Okay, and in this case, we have these spatial weight functions. Okay, and there are many, but the commonly used ones are contiguity based and the distance based. But all these are based on the semantics of the objects. For instance, for aerial data, spatial data, you can use the Rook's case or Queen's case contiguity matrices or functions. But for distance, let's say if you have let's say groundwater, which are which are systematically distributed, then you can use the groundwater, the distance-based weights. But the how to do this one here, there are several methods. But what is important here is to make at least, the standard approach to verification of Toppler's first law before you go into detailed analysis or understanding of the content of the data. Then you can use the similarity. That means the degree to which characteristics at one location are similar or dissimilar to those nearby. Or you can use the probability. That means you measure the extent to which occurrence of an event at one location makes more probable the occurrence of a similar event in a neighboring geographical area. But the famous one is using the correlation. Okay, and in this case, your correlation of a variable with itself through space. And this is what we call the spatial autocorrelation. That means you look at what we observed, especially in events which are continuous, in the geographical phenomena which are continuous in nature, like groundwater, because we don't know exactly where the source is, but it is the same, let's say, aquifer, and then you do observations and you don't know where this has originated. So this has been the best and applicable approach, whereby you can use the you can test the self-dependence. And because of the nature of the phenomena, you can just constrain by looking at this self correlation. And now, how do we do that spatial autocorrelation? There are many approaches, but the famous one and the commonly used is the global Malan's eye. And here in this analysis, we have the hypothesis. That means we consider that the standard irregularity conditions are valid, meaning that there is a completely spatial randomness causing the process, causing what we observed through the measurements which we did. But the alternative is either dispersion, meaning that heterogeneous process, or it is clustered, meaning homogeneous. I will talk in details about this one here. But generally, what you test is the Moran's eye statistics to see if it is significant. If it is not significant, then you have to use the standard approaches or standard methods. But if it is significant, then you need to go for advanced methods. Okay. And now, if it is significant, we have you have to analyze the spatial clusters, because you have homogeneous and you have the heterogeneous. That's what we call the spatial cluster and the spatial outliers. So there are some techniques, but the famous one is the univariate local Malan's eye statistic, whereby the observations, you divide your observations into 4 quadrants. Okay, the first one, it is the quadrant with the high surrounded high values surrounded by high values. The second one is low values surrounded by high values. The third one is low values surrounded by low values. And the fourth one is the high values surrounded by low values. So these have implication on the processes which are characterizing the phenomena. But now you can perform also, you test the significance of what you see here. And when there are significant, and then you can go for modeling. Okay, in this case, we are talking about the spatial modeling, meaning that you have to incorporate all, the spatial dimensions in your model. For instance, here we have the spatial modeling. We have the spatial Lager model. Okay, you can see how we formulate, but we have also the spatial error model. Okay, but here we have these parameters, which are, we call them the spatial autoaggressive parameters. Okay, these parameters will always indicate whether the class, the autocorrelation in the error term, the autocorrelation in the error terms, or the autocorrelation in the observed events or the measured values. And if they are significant, that means you have to if they are significant, that means you have to adopt the spatial modeling approaches. But if they are not significant, that means you can go on this side and do whatever. Use the regression, let's say regression analysis, using ordinary least square estimation, and you end up with the results whereby you can inform what is happening in the environment. But we have how to collect the data, spatial data, in groundwater quality studies. Okay, and we have these standardized forms, which I believe every person uses this one here. But what is important? Here we have latitude and longitude. This is the location, because most of the researchers do ignore this point. This point, and that's why sometimes it becomes difficult to understand to understand the processes and the nature of the distribution of these processes. So for any data to be recorded or to be realized as the spatial data, then we have to make sure that we have accurate and precise measurements on the location whereby we get the sample. And then the rest of the parameters depends on what you wanted to see, can be fed in this standard form. So this is the kind of the spatial database in groundwater quality. So here you can see on this part we have latitude and longitude. That means this is position or location, which I was talking about. And the rest are some of the water quality parameters, okay, which have been organized, and every observation recognizes its neighbors, okay, meaning that you have X and Y, but you have attribute information at that particular location. But all these observations, they know each other, their location, through the topological relationship. But with this one here, it is difficult to understand the processes or to understand the nature of the distribution. So that's why we go to the, you need to apply the spatial analysis approaches. I have the case study in water sector of Tanzania, whereby this has been applied, and we have provided insight into what was known. This is a fluoride map in the northern part of Tanzania, and this is the nature. You can see here it is highly skewed, okay, meaning that some of the researchers do transform this data, and they forget that there is a spatial autocorrelation, because spatial autocorrelation, if it is serious, it is significant, no matter how you transform, it will always exist, and it will always inflate even some parameters like the R adjusted R square, which is the commonly indicator of the goodness of the model. Then it will be inflated in the presence of the spatial autocorrelation. Okay, so if you look into this point, groundwater sources distribution, so you can see some of the extreme values, that is above 80.84, they're not shown on this diagram because they are extreme. But what is, if you look on the map, you can see they pretend to cluster in some locations. This is one of the clues for a researcher, that okay, maybe there is something happening why these high values or extreme values are located in one location. Okay, but when you look into this map, this has been analyzed. This is a spatial map, okay, whereby we have incorporated the spatial, the spatial structure in the observations. And finally, because we are working with GIS, if you link with the tectonic setting, the tectonic layer or geological layer, you can see the high pattern is along the boundary between the two tectonic units. This is the volcanic rocks, and this is metamorphic rocks. Okay, so at the boundary, that's where these patterns are happening. So it is a reflection that tectonic processes are also highly contributing to this one here, apart from other natural processes. But also we have another pattern here, which is around another volcanic mountain, and in that case, and it is dominated by volcanic ashes. So in that case, you minimize the uncertainty about the something which has been there. Fluoride in Tanzania has been there for since 1930s, but it was not exactly known. But the other good thing, you can see some other low patterns, okay? And if you look at this, by interpretation of this, by looking at the WHO guideline value, in the low, all of the values, all the sources have low concentration of fluoride. And in that case, they can be the primary source for drinking water, because all the sources here, they have less than 0.5, 1.5 meters. But we noted another problem, because there were extreme locations with, there were locations with extreme concentration less than 0.5, which is also not safe, because it can cause prolonged exposure to less than 0.5 milligrams per liter for a long time. Then it can lead into dental caries. So that means even the water supply authorities, they are informed about this problem, which should be taken into consideration. But here, through the use of GIS, that means we are trying to interpret the results of the analysis, because we depend on one variable, but we now optimize our understanding through linkage with the geology. Okay, you can see here, the probability of targeting safe water in hot and cool spots. Here, the hot spots is about the high, which are shown on the map. But you can see different geological layers with different probabilities of safe and unsafe water. And in that case, we can improve even the drilling, the issuance of drilling permits in Tanzania through the use of this approach. But here, this is what I talked about the problem of dental caries, because most of the sources in the low areas, they have concentrations less than 0.5. So this also presents another problem of dental caries, unless these people living in these areas are supplemented by some other sources which can at least give adequate concentration for human health. For this one here, it is the spatial pattern, because we wanted to map even the risks. Okay, so through the use of spatial analysis, especially on this one here, we calculate the risk. That means we calculate the probability of having fluoride less than, greater than 1.5, and then it times the total population. And finally, we end up with this pattern high. It implies that this area, actually, when you look into the Rift Valley, it is within the graben of the east of the Rift Valley, and it is a reflection that groundwater, they are accessing groundwater from the sources which have, where groundwater has been into contact for a long time, and that's why you have this you have the risk areas within the graben. And as part of the validation, we took some photos in the field. You can see in these areas we refined such kind of people, and you can see these are just the school children which are highly affected. Not only even fluorides, you can see even some have developed bigger heads because of the dependent on fluoride contaminated water. But also through the integration of GIS, you can even estimate the number of population which are now at a risk and are already some are already affected. You can see in this area you have around 2 million people who are at a very high risk in terms of fluorosis. So the final one is the demonstration of the spatial modeling results. Okay, here you have on the left-hand side map. It's just a simple ordinary least square regression model results, and the right one is the spatial lag model results. You can see the difference between these two maps. Okay, and whenever if you account for the spatial effects in the model, you can enhance even the pattern. So here you can see that around, the patterns, for instance, here, what as part of the validation, we noted that this pattern in yellow is just following some rivers. Okay, that means rivers from around this mountain, Mount Meru, then flowing downstream, in the southern part. Okay, and of course the area is dominated by volcanic mountains, minor volcanic mountains, and which act as the secondary recharge areas. So there is a mixing of water along the river, and that's why you find some less concentration, relatively less concentration compared to areas, to the sources away from these river valleys. Okay, but so in this case, you can even advise the decision makers or the service providers to enhance their services through these maps. I think this is the last slide. You can conclude the presentation. Thank you so much for listening.
Yeah. Thank you very much, Julian. So I think the next slide is. Thank you very much. I think there must be questions, so we can now take up the questions.
Thank you, sir. Dr. Julian, I am thankful to both of you that you are giving a very nice and informative lecture, and you have managed the time as well. I think all the participants got the exposure about this groundwater contamination, and this will definitely help in their future research. Sir, I'm thankful to you again. Now I ask the participants to raise their hands if they have any questions.